Welcome to today's webinar with the title Additive Series Process for Flexible Solder Mask, our new standard. I'm Andreas Schilp, the moderator of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speakers of today's webinar are Jürgen Wolf, Head of the Advanced Solution Center, Markus Kennert, Team Leader Production and responsible for through-hole plating, solder resist, screen printing and surfaces, Hans Fritz, Managing Director of SAT GmbH, Takayuki Hidehira, Executive Vice President of Microcraft. And now, I wish you lots of fun and new information.
Thank you, Andreas, for this kind introduction. So what do we want to show you today? So first of all, we dive into the field of flexible solder resist. I want to explain what it actually is if you do not know already. We will show you how up so far we realized flexible solder resist on our printed circuit boards. Then my colleague Markus will take over and he will dive into the flexible solder resist applied by additive technology onto the PCB. He will show the process flows, the procedures. We will do a short technology comparison between our conventional process and the new process. And then we will hand over to Hans and Taka-san to show the equipment, the machine, and to show the flexible solder resist. And in the end, we will have a short summary. In between, you will get 2 poll sessions where you can basically answer questions from us in multiple choice. So flexible solder resist, what does it actually mean? Well, there are common industry terms for it. Some say flexible lacquer, flexible solder mask, or flexible solder resist for it. The flexible solder resist basically serves different purposes when applied onto a printed circuit board. It basically is a protection of the copper structures in bendable areas of flex rigid with external flex buildups for flexible PCBs and for semi-flex PCBs. For those of you who do not know semi-flex PCBs, well, it's just a multi-layer FO4 board, but in specific areas the FO4 is milled down to precise thickness so that you can bend the FO4 for very low bending cycles, basically for flex to install applications, so that you do not need to use an expensive polyimide in your build-up. Then standard flex to install with polyimide, there you have multiple bending capability. You use it to have small bending radius. Then you have a defined transition between the rigid part of your PCB and the flexible part of your PCB. And in a lot of applications, you can use the flexible solder resist to replace the expensive polyimide coverlay, which is partially applied. It is a foil basically. Normally, you have to cut it out. You have to manually align it on the board. And the flexible solder resist is completely machine applied, so you have a lot of advantages here. So what did we do in the past? Well, we were using screen printing processes to apply the flexible solder resist. And to do so, you first have to create your screen. Then you have to pre-clean the board. Then you go to the screen printing process where you apply the flexible solder resist and print it through the screen onto the PCB. You thermally cure it in an oven, and the screen themselves, they can be reused, but you have to wash them, you have to clean them, you have to remove the agent on the screen which you use to print. So it's quite a lot of process steps to do this screen printing. So then I hand over to Markus and he will introduce you to our new additive process.
Hello too from my side. Nice to meet you. My part is the flexible solder system additive technology. In the first step, the process flows. We have to pre-clean every time in every technology. We have to pre-clean to have a good surface without any residues or anything. So and we to increase the Haftung, the adhesion. So afterwards we can print it per inkjet. We have a UV curing step. This is always the same step, and then we have the thermal curing similar to the standard process. So we have only 4 process steps. Further, we have the question how to print. Schematic illustration we have now here in green the PCB or the panel, the production panel we use in 2 different views, and on the right side this big black block it's the print heads, the UV trap, and the LED source we have. So and now I start. The basic procedure is first step printing, covering of the edges. The first step is an important step, but also important is the second printing step, filling of the flex area to get this layer thickness we want to have. So you see now this hardware, this 3D, this LED 3D printing with multiple printheads in parallel with UV LEDs and the printheads behind the cover. It's a 4-head machine. So now we have a look on a live movie we made in the production. So we start the vacuum table, the production panel will be moved on it. Then we have to look if the panel is clean. So we have a cleaner roll we put on it, and then we start the data. The machine starts to produce. The first step is the alignment. You see in the left corner the alignment crosses. So 4 alignment marks will be searched and will be found. So and afterwards the printing starts. We print in stripes. So you see the machine making stripes which are printed. So the first layer is printed right now. So the second layer begins. And after the second layer, we have a step, a UV curing step. So second layer is nearly done. And now we have the final curing step in the machine. So it's afterwards tech-free. We can handle it normal as a normal panel. Going to the oven. So the pan is ready, 1.5 minutes. A tech-free layer we printed, nearly perfect. So a comparison of the 2 process flows. We have less steps, only 4 steps, and we have a win in time because we have no screen. We don't need to create screens. Yeah, we have a faster production, so we get a better delivery time, I think. Now you see in the left side the machine from the CraftPix machine from Microcraft CPQ 7861. We use a flexible solder resist ink from Microcraft MPJ 101 FG20, a UV and thermal curable inkjet solder resist. So now my colleagues from SAT, Hans Fritz and Takasan, now it's your turn to give us further informations to the machine, to Microcraft, and to the ink.
Thank you very much. Nice to talk to you. SAT is representing Microcraft in the Central Europe, and who can explain the technology better than Microcraft? Taka-san. I would give the word to Taka-san.
I'm Takayuki Hidehira from Microcraft. Nice to meet you. So Microcraft is a Japanese company, and we have been making inkjet printer for almost about 20 years, focusing on the electronics industry. And we first started legend printing application and later expanded the application to the solder mask printing. So let me introduce one of our inkjet printers, which is CPQ7861 with 4 print head arrays with a very fast nozzle. And also we have a automated maintenance feature to maintain the quality of the printing. And also we can choose the printing resolution by software configuration. And also using the software, we can have the serialization and also barcode in the printing. And we have the printer is equipped with a table which has a vacuum and also edge clamp to hold the material. And we also have an optional loader and unloader machine. Yeah, and this is about our ink MPJ101 FG20 is the flex solder mask ink for inkjet. We also develop this ink on our own, and this ink is specially designed for our CraftPix series. So, and this ink is UV cure type ink, which means we can put the ink and soon after we can cure with UV. And also, we recommend the surface treatment before printing to get better adhesion and also create a more clear picture. Okay, then we can also print this inkjet ink on the polyimide and also flex rigid PCBs, and of course on metal like copper and also plastic substrates. We have the ink is certified with a UL94 V0 test.
Next slide, please.
Yeah. So this table is from the technical data sheet of our ink, and we have tested the standard IPC standard tests, which are adhesion and also the heat resistance and solvent resistance and plating resistance. All tests are passed. Yeah, so there are several more testing results, which, for example, like dielectric strength and insulation resistance, which are also, these are also from IPC standards. And as I told, flammability test. And we have also tested the bending test, like, yeah. And also the thermal shock. So basically we did these tests based on our customer's requirement. And as you see, the ink is ready for the production.
Great, thank you, Taka-san, and thank you, Hans, for the kind introduction of your machine and your flexible solder resist. And it's really an honor to have you here today with us. This was on a short term. We just last week met each other and had the idea, why not joining you two guys? And I'm really happy and proud to have you here today. Thank you to you over to Bavaria, where you're sitting at the moment.
Yeah, thank you for the great opportunity.
Thank you all from my side.
I would just want to move on and show a little bit. Taka-san already said that the bending behavior is rather good, and we did some additional tests above IPC. We have internal standard tests where we look how far we can go. And for example, one test is to store the PCB with the printed flexible solder resist at 125 degrees Celsius for hundreds of hours. And after specific time slots, we take out samples from the oven and have a look on how they behave in the bending. So the IPC itself has a diameter of 3.12 millimeter, I think it is, 1.8 millimeter. We are going down to already 1 millimeter, which is a much more critical bending radius. And we could see that after 500 hours, we can still do 25 cycles in a 180-degree bending around this 1 millimeter pin. And we always check for cracks in the bending area for sure to see how the performance of this flexible solder resist is. We have seen that when you compare it to our existing solution, the screen printing solution, here we already had cracks after 250 hours when we did those 180-degree bending cycles. And this new flexible solder resist applied in the additive technology, we could reach 300, 400, 500 hours and still could do those bending cycles. So we have a much better performance of this new resist compared to the old screen printed resist. And to be honest, the old screen printing resist, it was a good resist. So it was a well-known industry standard and had good performance, but this new resist even tops it and is even better than the existing one. So as already addressed, I have a short poll for you, and I would like to know, at the present, we have a distance from the copper structures to the flex rigid transition. This is 1 millimeter or 1000 micrometers in our standard design rules. We would like to know which value would you like to see for a new process when we look on miniaturization. So what was your preferred distance, or what would you like to have from a new process? And Andreas, could you please switch over? And as I said, it's multiple choice, so you can choose between 1 millimeter, 750 microns, 500 micrometers, 400 micrometers, or even below less than 400 micrometers. So make your choice, please.
Yes, we are already busy. Half of you have already voted, so we will wait another 10 seconds roundabout, and then close the poll and show you the result. Okay. Few more seconds. And then I will close the poll. And this is the result. Erik, what are you thinking about that?
Interesting, because it's almost the same percentages than in the German webinar, which we were having in the morning before this one. And it's the same result. So most of you wish to have 500 microns. So half of the actual standard at the moment. And what is interesting is that some of you even want to have less than 400 microns. So let's switch back and have a look directly into our new design rules. So when you go onto our website, you can download our design rules. And I just picked one example. It's the 1F XRI design rule set. And when you look into our design rules, you will find this letter G, which describes the distance from the exposed copper to the flex rigid transition. And as I already said, our technical standard at the moment is this 1 millimeter. And when you look on the new flex solder resist, you see that especially for the advanced requirement, we could reduce it by 50% and could go down to 400 micrometers. Our technical standard at the moment would be 800 micrometers. And when I think back to the poll, you see that those 500 micrometers, which the most of you were wishing for a new process, we can fulfill this now with the advanced requirements. And to be honest, we do not yet know the final limitation of the process. So this in future will go down as well, but at the moment we set it to this 800 in the standard and the advanced requirements with 400. For testings, we even had samples in the production where we went down to 200 micrometers or even to 100 micrometers, but this is something we still have to look on to a little bit more. So at the moment, starting with today's webinars, and you will find this updated information already on our website, we have the 800 for the technical standard and advanced requirement 400 micrometers is possible starting today.
So,
sorry, we had when you look on this higher accuracy here, you see this picture where we even went closer to the copper transition. So this is not standard and not advanced. This is only 100 micrometers. So this is something which you will see in the design rules in the future. But this new process really helps us to reduce the distances of the flex resist to the copper, and thus we have less overlapping from the flex resist to the rigid resist. In the existing solution, when we did the screen printing, well, the screen printing process is a rather high tolerated process, and therefore we had to use this 1 millimeter because of these high tolerances in the screen printing process. It's not a very accurate process doing screen printing, and going into the additive technology, we can be much more precise, and therefore we have a higher accuracy. When we reduce these distances, for sure, you can have more available space in the rigid area. So you can put more components and more copper structures in the rigid area, have a better usage, especially with narrow layouts. And as I already said, this distances, we will reduce them in future much more, and we will see where this is going to head in half a year, 1 year. So it's still an ongoing process, and it will be interesting to see what will come out.
So we have now a look on a detailed, or have a detailed view on it. Yeah. For example, in a micro section, we see some layer thicknesses, as you see here. Important for solder resist, also on the flexible side, is the coverage of the cover structures. The edges are the most important points on these structures. So you see on the surface around about 50 microns between two lines. You have a coverage of the edges of 15 microns and 25 microns on the copper structure. As we see the overlapping of the flexible area to the rigid solder resist, you see a good coverage, a good overlap, 23 microns overlapping thickness, and on the left side 45 microns on the surface. That's the layer thickness without copper, because some ink is flowing down between these copper structures. So, but it's 50 microns is a standard layer thickness we have also in the silkscreen production. So next step will be a process comparison of us. Different steps, different things we viewed, number of process steps, equipment costs, resist costs, the screen preparation costs and the screen washout costs, which is a part of us. We need to have this information, And we have some things from of the environmental view, resist waste and energy consumption. We have a look on it in a comparison. So conventional process steps, we have more process steps as in the digital additive process. And we have this screen print, washing and build up. So it's a matter of time. We need 3 days to have a good screen at a department. So we have to plan it before these 3 days. With this digital additive manufacturing thing, we have the data is putting to the machine and is printed, and the pen is ready. So it's a matter of we need less time. The equipment costs are higher in a digital additive way because of the machine. One printhead costs about 10,000 to 15,000 euro. So conventional, you have only a silk screen machine and an oven, more or less. So it's a little bit cheaper. The resist costs are also better because the ink is standard ink in the silk screen technology. So it's less price. You have a cheaper price of it. In the digital additive manufacturing thing, it's a thing of the amount of ink you produce and we produce, so it's not so high. So the costs are per kilogram higher than of the standard silk screen process. The screen preparation costs are better in digital additive because we have no screen. So we have to prepare screens, and there are high costs of it. Also, the washing of the screens is very expensive in comparison to digital additive, where we have no screen, I said before. The resist waste, so in this conventional way, we have high costs because we need more of this resist. Some amount of it is in the screen, which is thrown away. The advantage of digital additive is we print only where we want to print in this amount we have to print. So it's a very resist, or it's a very good way to print flexible solder mask. The energy consumption, as it's better than in the digital additive in a new way and as in a conventional, because these screens have to be built, so it's a very energy. The energy consumption is very high in this silk screen process. So as we see, equipment is very costs a little bit, and the resist costs are high. It's a cost neutral process, so we have no advantage of it. It's not, the costs are there, but we have a more sustainable digital additive process, which is the future process. So the next step will be a quick poll. The question to you is, what further developments would you like to see from us on the subject of flexible solder resist? So we have 4 points. As a cover replacement on internal flex with rigid flex, even smaller distances to copper structures, also replacing solder resist in the rigid area, or others, then please specify in the question box. Thank you very much.
Okay, the poll is active. You can make your choice, please. We already have some of your votes, around about 40% actually. So we will have another around about 10 to 15 seconds to make your choice. So actually, there is no special question in the question box by now. Okay. I close the poll and show the result.
Yeah, interesting. So it's all of the three given answers are used almost the same. We have a slight winner with also replacing solder resist in the rigid area. Yeah, so all of these developments are points which we are actually looking already at the moment. So coverlay replacement is a project going on, and so yeah, thank you for your feedback. So this shows that we are not heading into the wrong direction, and definitely probably several of these points will be present in the future as well. So we are working on it. So thank you for these answers.
So let's have a small summary of the key points. The flexible solder resist applied via inkjet represents a digital and additive technology, which is the future technology, in my opinion. Meets all common flexible solder resist specifications. It's a solder resist, so all tests we have done were with IPC standard to specify a solder resist. The specialty is here the flexible solder resist. We have these bending tests done. We are going up to 100 bending cycles with this application. We are much better than the silkscreen technology. That is the performance of the silkscreen technology. This is still good, but we have even better technology right now with this inkjet solder mask. It offers minimal thickness variation, and we have all possibilities to print where we want to print in the amount we have to print. It can be combined with legend printing. So if you want it, we can do it. And it promotes greater design freedom from reducing spacing requirements by half compared to conventional screen printing resists. And there is still a high potential to come up to 200 microns, maybe less. So in the future, a big thing. It provides higher reliability with higher bending cycles. So that's what I told you. It's really better than this old technology we use right now. So what kind of application do you have? How can we support you? More than you expect. So thank you very much.